Welcome back to ECE 320A. We're in Unit 9. Homework number 4 is, homework number 9 is due at the end of this unit. Exam number 4, it will be after Unit number 10. And Unit 9 is dealing with transfer functions, and in this video, what we want to focus on is the sinusoidal steady-state response. How do we use the transfer function to rather easily find the sinusoidal steady-state output response when we shake the system, when we excite the system at a particular frequency, let's say omega naught radians per second. So we want to, in this video, first simply state the relationship between the input waveform and the transfer function and what that produces in the output response in the sinusoidal steady state, and then we'll derive that particular expression. What we want to do then is use the transfer function, capital H of S, and we can find that for a circuit, we can find it for a more general system. Maybe it's a mechanical system, maybe it's an airplane, but we now have a transfer function which is associated with a linear time invariant system. We have this capital H of S, and we want to now apply as at our input sinusoids and see what happens to the output and rather quickly determine how to adjust the output by the impact of the system transfer function H of S. We know from the block diagram that the complete response in the S domain is simply the product of our transfer function and the Laplace transform of our input signal. If we want to go back into the time domain, that simply requires that we perform the inverse Laplace on all of that information in capital Y of S. That will give us the complete response. By that I mean it gives us the transient behavior, and if we have a steady state behavior, some kind of steady state behavior. In this particular case, we will have steady state behavior because we're exciting our system with a sinusoid that we never stop applying to the system, but we are assuming in this case that our system, H of S, is stable. That means all of the poles, if we found all of the values of our denominator polynomial, the roots of our denominator polynomial, those are the poles of our system, all of those roots of our denominator polynomial have to have real parts that are negative. We want all of the poles of our system to have values or lie in the left half complex S plane. We have this complex plane that illustrates the frequency content of our system. That's what S is. And we now sketch all of those X's associated with H of S. We want all of those to be in the strict left half plane. We don't want any on the imaginary axis. That's where the strict comes in. We want them to lie off of the imaginary axis, and none can have a positive real part. So we're assuming this is the key assumption, and the very first thing that you want to verify before you start applying this formula is make sure that the poles of your transfer function H of S are all stable. Once we have that, now we're going to excite the system with a sinusoid, and that sinusoid now is, so now we're injecting a sinusoid with a frequency of omega naught. The input waveform has an amplitude of A, and it also has a phase shift of phi. And we can write that then as an amplitude of A cosine omega naught is in radians per second, so that when we hit it with t, or multiply it by t, we get radians, and obviously then the phi, in this particular case, needs to have units of radians. We typically mix those, sometimes phi is in degrees, but if you're actually physically computing the cosine of that argument, you need to make sure that you're consistent with whatever omega naught t is producing and what phi is. You can't be adding or subtracting radians and degrees, that's not going to give you the correct answer. So if you have a degree value for your phase angle phi, which is common, then if you are computing that, make sure you convert that back to radians before you combine that with omega naught t. The second expression that I've shown you for x of t, it's equivalent to the first one, but here I've explicitly factored out the omega naught so that in square brackets I have t plus or minus this quantity that I'm calling tau hat, which is in units of seconds, and that's now, if it's a negative, that would be a delay in x of t. If it was a positive, then it would be an advance relative to where I've actually drawn my time t equals 0 location in the waveform. What we are going to now show is that if we excite this linear time invariant system that has a transfer function of capital H of S, if we excite that with a signal x of t that has an amplitude of A, an omega naught for a frequency, and a phi for its phase, then the sinusoidal steady state output, this is after the transients, which isn't very long in an electrical system, after the transients have disappeared, which is 5 time constants, then the sinusoidal steady state output will be the original amplitude of our input A scaled by the absolute value of the amplitude of our transfer function evaluated at or on the imaginary axis at a value S equal to j omega naught. Omega naught, again, is the frequency of our input waveform, and that's now what we're actually evaluating our transfer function at on the imaginary axis. We also will find the angle of our transfer function at that particular frequency, omega naught, and that will be introduced. I shouldn't put that you'll confuse that with a negative sign. We then add in whatever that angle is, whether that angle is a positive or a negative, we add that in to the argument of our cosine, and this is now how the output will be modified. Again, here's just our definition. We're finding the magnitude of our transfer function when we evaluate it at S equal to j omega naught. That just gives us a complex number, so we find the magnitude, we find the hypotenuse of this real part and imaginary part, we find the angle of this complex number by taking the inverse tangent of the imaginary part over the real part, and those are now our polar form complex number version of our transfer function. When we have this transfer function, let's say a group of poles and zeros, we evaluate those contributions of each of the factors in H of S at the frequency j omega naught, and that is then used in this expression to provide us with our sinusoidal steady state output. What we now want to do is go ahead and derive that sinusoidal steady state expression. Where did that come from? And before we get too deep into that, let me just say that throughout this discussion, we're going to use Euler, a few facts. Euler, we're going to use the cosine of two angles expression, and we will also use the relationship between the transformed version of a complex set of poles, and these complex poles are at plus and minus j omega naught, with this complex number for its partial fraction expansion coefficient. And here I've simply re-derived where that inverse Laplace transform comes from, or when you see now K1 as a complex number over S minus j omega naught. And remember, this is key. K1 here, without the conjugate, is associated with this pole factor, and if you find the value of S that causes this to vanish, that's when S is equal to j omega naught, so that now we are actually right here in the upper half of the complex plane. That's the pole associated with K1. We need to make sure that this is what we're talking about when we speak of K1. When we do that, now K1 is a complex number. It has a magnitude and an angle, which is what we're showing here. Then its conjugate just has the negative angle. We can plug those angles in as complex exponentials, and voila, we see that fact 3 says that if we want to take the S-domain version with these complex numbered partial fraction expansion coefficients above the complex pole locations or on the imaginary axis, we will have in the time domain 2 times the absolute value of K1 cosine omega naught t plus the angle of K1. Let's now see if we can use these facts to derive this particular expression. We'll start with what we know. We know the complete response is found by multiplying the transfer function times the Laplace transform of the input waveform. And again, the input waveform that we are applying now to the system is a pure sinusoid. It's, in fact, in this particular discussion, we'll just go ahead and use a cosine waveform at a frequency omega naught. What we want to do, though, is actually separate that complete response into two pieces, a steady state component and a transient component. So we now have a blue team and a red team. We're going to neglect the red team because when can we neglect the red team? After 5 time constants. It's already gone. And we've already assumed that capital H of S, our system, has all of its poles in the left half plane. All of those poles now will have negative real parts, so they indeed will decay with time after 5 time constants associated with the real part of their complex pole location. So what we want to do is actually not worry so much about the red team or the transient piece. We can neglect that. We want to focus on the blue team, which is the sinusoidal steady state component of the complete response. We want to now see, can we actually find capital Y sub SS independent of the red team? And in fact, we can. So we want to now derive or find little y sub steady state of t. We know what we're going for. We've already shown you the expression. But we now want to find capital Y sub SS and then see how that leads to the expression that we know that we want to determine or find. And we want to do that without having to play with the red team. We want to find the Y steady state of t without having to find the complete output response. You could find the complete output response and let t go to infinity, and you will simply have the sinusoidal component, steady state component left. All the other pieces will decay. And that's what the transient means, or that's what it does for us. So here's where we're going to start. We'll try to find little y sub SS of t. Again, we're shaking the system at a frequency of omega naught radians per second. And we're going ahead and trying to be as general as possible. We're saying the amplitude of that input waveform is A, and the input also can have a phase shift, just meaning that wherever we've decided to draw the time t equals 0 location, maybe now with phi, that just means that the peak of our cosine is going to be shifted away from time t equals 0. That's all that's saying. We still have a cosine of frequency omega naught and an amplitude of A. So let's rewrite x of t by using rule number 2. And if you've forgotten rule number 2, that's just the cosine of a sum of two angles, which I've repeated here. But now one of the angles is omega naught t, and the other angle is phi. So if we apply that formula, that's what we end up with. We now have a two-piece expression for little x of t, the signal that we're using to shake that waveform. So really, when you have this phase shift phi, that's like saying, oh, we have a shifted cosine omega, or an amplitude changed cosine omega naught t, and a combination of a sine omega naught t. So we have some linear combination of sine and cosine at this same frequency omega naught t. That's all that phase shift is really doing. What I'm doing in the next line is simply explicitly recalling or reminding myself that cosine of phi is a fixed angle, so cosine of phi is a number. I'm simply combining that with the constant a, so a cosine phi, that's just a constant, and then the minus a sine phi is another constant, so really I simply have a weighted cosine omega naught t combined with a weighted sine omega naught t. Again, I haven't changed the frequency, I just now have a linear combination of sine and cosine that are present because of this phase shift. If that phase shift wasn't there, obviously I would just have a cosine omega naught t. By including that phase shift, it's now a more general derivation, but that simply says that I'm still shaking the system at the same frequency, omega naught, in both the cosine and the sine. That's in the time domain. Let's go ahead, because we like to work in the frequency domain. We like to run over and be in the frequency domain because that makes our life a little easier. We can now play with algebra instead of having to worry about differential equations and time domain solutions and maybe even convolution. But don't forget convolution. You need convolution for the rest of this class, and it's a nice concept to have in your back pocket until you finish your career as an engineer. Let's now Laplace transform little x of t, and hopefully you remember what that is. Now we can simply Laplace transform cosine omega naught t, and that is now just s over s squared plus omega naught squared, but we have to weight that by a cosine of phi. And then let me go ahead and pull the negative sign out, and we have the Laplace transform of sine omega naught t, which is omega naught over s squared plus omega naught squared. And again, we have to scale that by a sine of phi. If we want the complete solution, we can get it. We simply take x, capital X of s, which we now have in the frequency domain, and hit it with the transfer function capital H of s. And that's exactly what I've done in this line. The only thing, now that I have this dashed highlight around the denominator, what I'm reminding myself of is the fact that s squared plus omega naught squared can be factored into its two pieces, where one factor has a root at plus j omega naught, which is what I've highlighted in red. That's the pole factor on the plus j omega axis. And we have another pole factor, or a pole factor, where s equals minus j omega naught would cause it to vanish. We now have poles in the complex s-plane. One is at j omega naught, and the other is at minus j omega naught. This is the s-plane. These are the poles due to our input waveform, and this is the factor for that pole, and this pole is associated with that factor. And we want to really focus on the yellow highlight. We want to worry about s minus j omega naught, because remember, that's what the K1 is associated with. K1 conjugate is associated with the blue highlight. We want to focus on the yellow highlight. Again, and I didn't stick with my color coding, we have y steady state, which is blue, and y transient, which is red. We're separating the complete response into its two pieces, a sinusoidal steady state piece and a transient piece. And the transient piece is due to the poles of capital H of S, which we are assuming H of S is stable. So those disappear after 5 time constants. I've partially, with the partial fraction expansion, stuck with my color coding, but I failed to keep this red, but that's now the red piece, and that's due to the stable poles of H of S, and those will all decay with time. So as time gets large, and it doesn't have to get that large, infinity now is beyond 5 tau, which isn't much in an electrical sense, but now we've identified this expression y sub ss that we, capital Y sub ss, that we want to focus on. And in particular, we want to find an expression for k sub 1 in terms of the different variables or parameters associated with our system, H of S, and the excitation, which is at a frequency of omega naught. So let's now dive into that. We can solve for K1. It just is a unique pole factor, and we can use the cover-up method. So now let's solve for K1. We simply multiply all sides by the factor underneath K1, which is S minus J omega naught, and multiplying that on the left, multiplying that on the right, all of those disappear when we let S equal J omega naught. Those all vanish, and we're just left with S minus J omega naught times Y of S, and we want to now evaluate that at the pole in the upper. We're evaluating it here. That's where we are evaluating with our cover-up method. Let's now replace capital Y of S with what we just found. Here's capital Y of S. It's H times this blue piece, which is associated, or the Laplace transform of our time domain sinusoidal excitation. And we want to evaluate that now at S equal to J omega naught. Meaning, everywhere we have an S, we replace it with J omega naught. So H of S gets evaluated at that location in the complex S-plane. We evaluate H at J omega naught. That now is a complex number. This particular term in this expression for K1 is a complex number. We're simply plugging in everywhere we have an S in H, we replace it with J omega naught. Then in the curly bracketed piece, which are the terms associated with our excitation, how we're shaking it, X, capital X of S, we replace S with J omega naught. We now have replaced it here, and we've replaced it in the denominator. And let's now identify or start to see if we can clean this expression up or simplify it a little bit. And it looks like we have a lot of J omega naughts floating around. We have a J omega naught in the first term in the numerator. We don't have a J omega naught yet in the second term in the numerator, but we can introduce a J if we rewrite minus 1. J is the square root of minus 1. So let's now replace this negative sign with a positive sign and say that that's now J times J. J times J is minus 1. So we can now say that the second half of the numerator is plus JJ A sine phi omega naught. And what do we now have? Well, we have one of these J omega naughts and another one of those in the denominator. So effectively, we have 2 times J omega naught downstairs. We have a J omega naught here. And if I now combine this j with that omega naught, I've now canceled all of the j omega naughts, except I'm left with one of these j's right here with the plus sign. Hopefully you're following me. So let's now write down what we've now uncovered in all of this analysis. We have a capital A in both terms in the numerator, so that can come out front. We can say we have an A times an H of j omega naught, and downstairs we're left simply with a 2. That's the red 2 up above. What's left in the curly brackets? Well, we've factored out the A, and the only thing we have in the first term of the numerator is cosine of phi. And the second term, we have a plus j. We factored out the capital A. We have a plus j sine of phi. And now that should look very familiar. That's now rule number 1. From Euler, we know this is now e to the j phi. I think I called that rule number 1. So there's rule number 1. And now we can rewrite K1 in a little bit more compact notation. We can say we have A over 2. A, remember, was the amplitude of our excitation signal, little x of t. H of j omega naught, that's our transfer function where we've replaced s everywhere with this complex number, j omega naught. So h generically is complex. And then we hit it with e to the j phi, this complex exponential where the exponent is j phi. And what I want to do now is simply rewrite h in a polar form, knowing that it's a complex number. If h of j omega is complex, let me go ahead and write that as a magnitude at an angle. So that now when I see h of j omega naught, I'm going to rewrite that as magnitude of h at j omega naught, angle of h of j omega naught. That's the polar form. Just look at a hypotenuse at a given angle. That's a complex number that is associated with our transfer function when we evaluate that transfer function at a particular point on the imaginary axis, and that point is j omega naught. And let's also define this angle of h as a theta, so that we can maybe clean this up a little bit more. So that now we can rewrite K1 using this polar form version of h, the complex number. So h of j omega naught is magnitude of h, j omega naught, e to the j theta. And that's really all that angle of h of j omega is. It's now e to the j theta. We could write that in rectangular form if we wanted to. That's now magnitude of h times the quantity cosine of theta plus j sine theta. But we're going to go ahead and leave that in polar form because that allows us now to play with the exponentials. Or now K1 is a over 2. We haven't changed that. Magnitude of h of j omega naught. Then we had an e to the j phi. And we also had an e to the j theta omega naught. That was due to the angle of h. That's what this is. Theta of omega naught is the angle of h of j omega naught. So we just look at the imaginary component over the real component and inverse tangent that, and that will give us this angle. So now we have K1, and we can actually say that K1, we can combine those exponents. We can say that we now have K1 as a over 2, magnitude of h of j omega naught, e to the J phi plus theta omega naught. That's what K1 is. K1 is a complex number. Has a magnitude of AH over 2, where H was the magnitude of H, and it has an angle of phi plus theta. And we can now invoke rule number 3 to immediately go into the time domain once we have K1 identified, which we now do. K1 is now identified in terms of the system's transfer function H written in polar form. So y steady state, because of rule number 3, is simply 2 times the magnitude of k, and we know what that is up here. We know the magnitude of K1 is just that, and we know the angle of K1 is this. So now let's replace that with these particular factored forms of K1. So K1 is a complex number. We replace that in this expression for y steady state. We have 2 times the magnitude of K1. Well, K1 had a magnitude of A over 2, magnitude of H of J omega naught. Then cosine omega naught t plus the angle of K1, but the angle of K1 is phi plus theta omega naught. Again, this is just the angle of H of J omega naught. And this phi, remember, phi was the phase of our original excitation, x of t. And we can clean this up a little bit. This 2 cancels that 2, and now we have the formula that we had set out to derive. We now know that y steady state, after the transients, when we shake this system with a signal A cosine omega naught t plus phi, after the transients, we then end up with A scaled by the magnitude of our transfer function at h of j omega naught, cosine omega naught t plus phi plus theta omega naught. And that is now the formula that we set out to derive, and all of that now is a result of shaking the system with a frequency omega naught, an amplitude of A, and a phase shift of phi. You can see where those pieces now come into the sinusoidal steady state output. Then the sinusoidal steady state output has to account for that sinusoid passing through the system, and the system now changes the magnitude by the magnitude of h at j omega naught, and it changes or it shifts the time domain waveform by an angle theta of omega naught, where theta again is the angle of h at j omega naught. Summing that up, applying a signal A cosine omega naught t plus phi to a system that has a transfer function capital H of S, the amplitude is simply changed by the magnitude of H evaluated at j omega naught. The phase of our sinusoidal steady state is modified by the phase of our transfer function H of S when it is evaluated at S equal to j omega naught. So we want to find the sinusoidal steady state output due to a input sinusoid. We simply evaluate the transfer function at the excitation frequency. That produces a complex number. We find the magnitude of that complex number. That gives us how the amplitude is changed. We find the angle of that complex number. That tells us how the phase is changed. And that now is a very powerful tool to know how the output or the system is going to perform or shake when excited by a particular sinusoid. Now what we want to do is figure out or start to analyze particular circuits using this strategy, and we will also investigate how we can maybe find not only this complex number h of j omega naught analytically, but also graphically.